That's right.
Do you remember those?
Well, I think Morris, Ronald, Cornelius, we're ready to start. We're very privileged to have Professor Lanczos visiting us in Manchester. He's a distinguished mathematician who needs no introduction at all, I think, to a mathematical audience. In the course of a long, and if I may say so, happily continuing career, he has touched upon mathematics at many points. In this discussion this afternoon between Professor Cornelius Lanczos, who is on my left, from the Dublin Institute for Advanced Studies, Professor Maurice Priestley, Professor of Statistics, one of my colleagues, and Dr. Ronald Butler, also one of my colleagues, and myself, we shall be covering Professor Lanczos's interests, his contributions, and his views as regards mathematics. And I'd like to begin myself, I think, Cornelius, by asking you a question, and it seems to me very appropriate to begin with raising the question of the relationship between physics and mathematics, and the effect of the one on the other, the effect of physics on mathematics, and also the effect of mathematics on physics. This, I think, is a very interesting question. It's a question that I think nowadays pure mathematicians, perhaps on the whole, tend to reject as being of no significance whatsoever. But for applied mathematicians, I think this question has the greatest significance. It's intrigued many people, I think, over the years, and in more recent years, more recent times, perhaps the names of Richard Courant of the New York University Institute for Advanced Studies, and John von Neumann, who was at Princeton, may perhaps particularly be mentioned. Now, what just is your view of this particular question, Cornelius?
Well, I like to see things in a historical setting, and historically speaking, up to the beginning of this century, there never existed this dichotomy between what we call pure mathematics in the sense as a kind of narcissistic enterprise of the human mind, that what we call today mathematics is considered as a logical enterprise where the human mind makes up its own laws and its own postulates, irrespective of what the physical universe is doing. But that is not the way how it happened historically. And if we go back to history, starting with the old Babylonians and Egyptians, and then later the Greeks and Pythagoras up to our days, we note up to the end of the 19th century, we notice that there was a very strong correlation between mathematics and its applications to the physical universe, what they called natural philosophy. I mean, Newton would have not been interested in this tremendous discovery of calculus if it wouldn't have been directly applicable to the laws of nature, and it wouldn't have had such marvelous relations to the physical universe. And it seems to me, if you just take mathematics as a free enterprise of the human mind, you might ask, but why do you make up your postulates this way and not in some other way? We usually consider such set of postulates interesting, or any kind of postulates which are not self-contradictory could be used, but we only consider those as interesting which are applicable to the physical universe. That's the way how we make up the postulates of algebra. And for a long time, for example, non-commutative algebra was out because one didn't see any applicability to the physical universe until the matrices were discovered, and one found that matrices are terribly important in physical problems, and so one had an example for non-commutative algebra.
Yes.
Or for the quaternions, which were also in connection with the space-time universe, the four components fitted so wonderfully in anticipation of the later four-dimensional universe. But all these discoveries, all the great discoveries of mathematics came not for the self-glorification of the mind by being in love with itself, but in view of the physical universe, the basic aim being to understand what to understand what's going on around us. And since it was realized that mathematics is the language in which nature speaks to us, and I think that was the basic stimulus in mathematical discoveries, starting with Pythagoras and his observations with respect to the triangle and the whole Greek geometry. After all, geometry, you might say, is a free creation of the mind, but it's not true because we live in a certain space, and we just discover the laws of this space. So it is not merely an arbitrary set of postulates. So I do believe that the problem of physics and mathematics always went together to a very strong extent, up to our century, when this very strong dichotomy started where practically everything which is applicable in mathematics is considered applied mathematics. And boundary value problems or elasticity, hydrodynamics, and so on is all considered not part of mathematics but part of physics. And mathematics is restricted essentially to a logical game. But this idea of a logical game, which is already creeping into the secondary schools even, is a new development. And I don't believe it's a necessarily very happy development. It certainly might have its great advantages, but I, in a certain sense, regret this very strong departure from the laws of physics when it comes to what we call pure mathematics.
Yes. This, of course, could be a swing of the pendulum, I suppose.
Yes, certainly.
And given
certainly.
enough time, the pendulum would swing back again.
Could entirely be. That's
Yes.
entirely true. This is entirely true.
It's often seemed to me to be a great pity that mathematical ideas produced by non-mathematicians, for example, the idea of the operational calculus coming from Heaviside,
Yes.
the idea of these rather peculiar functions, the direct delta function, coming from other people, that the pure mathematicians of the time, on the whole, did not pick up these ideas and make them respectable, put them into a really good mathematical framework. In the case of the Heaviside operational calculus, we had to wait a long time for this to be put on a proper footing, and the same one might say in regard to the direct delta function.
Yes.
It's only in the last decade or two
That
that
one
we had the
recognized.
theory of distributions by Lawrence Schwartz.
Absolutely. Yes, that's absolutely correct. Yes.
Yes.
So it can happen that a mathematical idea is tremendously useful in its physical aspects, and then you have to find its purely mathematical motivations.
Yes. Von Neumann, of course, felt very strongly about this indeed, and I read some very interesting papers by him, which in point of fact are reproduced in his collected works.
I see.
He felt very strongly, I think, about the widening gulf, I think as he saw it, and also as Courant saw it,
Yes.
between mathematics and physics.
In physics, yes. Of course, Johnny von Neumann was such a universal genius that he was completely at home in the so-called pure mathematics and also in physics and applied in every
Yes.
branch of mathematics. Yes.
And incidentally, of course, a countryman of your own.
Oh yes, yes,
Yes.
yes. I'm very proud of the fact that I'm a countryman of Johnny von Neumann. Yes.
Yes. Well, Ronald.
I think that you're probably best known for your work in applied analysis, which was a word that you, in fact, invented yourself, a term you invented yourself, and when you wrote your book of that name.
Applied analysis, yes.
Which is quite a well-known book. These aspects of your work started in 1938, I think, with your paper on trigonometric
Yes,
interpolation.
that's right, yes.
And then they carried on in many fields, including matrices, eigenvalue determinations, work on Fourier series, which Maurice will talk to you about later on. I wonder if you could, in fact, tell us something about this work, perhaps starting with how you discovered the economization of series at
Yes.
Purdue, what the people there, how they received it there, and possibly say, since all these aspects are in fact in applied analysis, could you say how the various places you've worked at have given you a stimulus
Yes.
in the various fields?
Yes, I might mention that it was more or less an accident that I drifted into these so-called applied channels. My basic love was always relativity and Einstein's work in geometry and Riemannian geometry and such things. But then during the war, I was already in the States during the war, and everybody felt that he has to do something for national defense. And the fact that I came in touch with applied problems and approximation theory, which essentially my book is devoted to approximation theory, but to call it approximation mathematics is a terribly long word. I in fact suggested the word parexic analysis because the word parexic in Greek means nearby, but it was not accepted. So when I was still in Frankfurt, and I worked in integral equations and quantum theory and relativity, various other fields, I had a friend, Otto Saas, who was a very excellent mathematician. And he told me about this remarkable non-orthogonality of powers. that we know that, of course, that the set of powers represent a complete orthogonal a complete set of functions. But the astonishing thing is what I heard from him, that you can leave out any number of powers and you still have a complete system. Now, if you have an orthogonal set, you can't leave out a single one because nobody can take over the job of the others. But with the powers, it was amazing, this flexibility. If you left out a power, you didn't lose anything. And you could leave out million, you could leave out any number of finite number of powers. For example, you could start from the millionth power and go up, and you still have a complete system. And you could leave out even an infinite set. According to Münz's theorem, if you do it properly, you can leave out a proper choice of infinite, and you still have a complete system. Now that brought me to the idea that powers are an example of the opposite of an orthogonal, of a tremendously non-orthogonal system. But if that is so, then it looks that x to the n could easily be replaced by lower powers. And if that is so, then a very long power series might be telescoped into a much shorter series. And now this is when I learned about the Chebyshev polynomials. This is exactly what Chebyshev found, that this Chebyshev polynomial Pn of x deviates from 0 by the smallest amount, and yet with the highest coefficient of x. That means if we want that the oscillations of this f of a polynomial should only be between plus minus 1, then the Chebyshev polynomials have the highest coefficient of x to the n, which means that x to the n is reducible to a lower power series with the smallest error. And that brought in the Chebyshev polynomials as a remarkable set of polynomials for reducing a long power series to a short telescope power series with the minimum error.
Were you then looking for these functions when you actually came across the Chebyshev polynomials?
Yes, when I came across, then I applied it immediately to certain power expansions. And naturally, if you want full accuracy, you don't gain anything. But if you have a certain finite series, for example, and you rearrange it with the help of these Chebyshev polynomials, then you found that the rearranged series converges very quickly, so that for a certain accuracy, you need only a very small number of powers. Now, that led very naturally then to the idea that what is a Taylor series? If you have a function which is defined by, let's say, a differential equation, then you can't satisfy this differential equation by a finite series. You have to use an infinite series. What happens if you use a finite series? Well, then you have an error term on the right side, and that error term is usually x to the n, or nearly some of the last powers of n. But now I found that this x to the n can be reduced tremendously to lower powers with the help of the Chebyshev polynomial. So I said, why shouldn't we put a Chebyshev polynomial on the right side rather than x to the n? And that had such tremendous results that I was myself completely flabbergasted when I first made these computations and found how the number pi or e to the x could be represented instead of the Taylor series by just a small number of powers, so that 6 powers usually gave you already 5 decimal place accuracy, whereas otherwise you would have needed maybe 20 powers or so. And that was the origin of my discovery with the Chebyshev polynomials, which turned out to be of such practical use that my work has been pretty much accepted in many countries. Particularly chemical engineers are very much interested. When I got these reprints, I got a tremendous number of requests for reprints from the part of chemical engineers.
And you were at Purdue University?
I was at that time in Purdue University. Yeah. So when the war broke out, and I got a call to the National Bureau of Standards to do some work in connection with war work, and naturally everybody felt his duty to do his work for national defense, and I gladly accepted. So that is the origin of my work in connection with these strongly convergent power expansions, which were exceedingly useful for almost any type of problems, one-dimensional problems, f of x and so on. For two-dimensional problems, the whole thing is much more complicated. Then, that was all based, of course, on this course I gave on approximation theory. It was an accident that I had to give to the students of the physics department a course on approximation methods. And that is where I came in touch with the whole field that we today call numerical analysis. And the basic origin of this Chebyshev polynomial which Chebyshev himself never used these polynomials in any practical way. That came through my friend Saas, and I remembered in our conversations way back in the 20s when he told me about the amazingly non-orthogonal properties of powers. And basically what I have done is to make the powers orthogonal with the help of these Chebyshev polynomials, which represent an orthogonal set of functions of maximum efficiency, we might say. And so that started out on my career in, we might say, practical or numerical analysis. And then after I made already my name, I just couldn't get rid of it. I mean, I always got various calls, not as a man who wrote in relativity, which was of no interest, but a man who had some papers in approximation theory from the standpoint of matrix. I mean, the matrix work came by my work for the Boeing Airplane Company. I mean, in elasticity, and when I got a call, that was a call I got in 46, that was already after the war. I visited Boeing once earlier, but I got a fixed call from a previous student of mine who was the head of the physics research unit at the Boeing Airplane Company. And I spent there 3 years. And I might say that the fact that I got so many different engagements or employments was tremendously helpful in enlarging my field of interest. I didn't know much about matrices, but then I learned tremendously about matrices in those days. And I liked from very beginning to look at the matrix from the standpoint not as an n by m, not as an n by n matrix as we usually consider it, but an n by m matrix, which shows at once that the matrix doesn't just transform a vector from one position to the other, but a vector from one space into a vector of another space. And therefore there are actually from very beginning two spaces involved, which you lose if you think of n by n matrices. Yes. And then in addition to that, I made the discovery that the so-called singular matrices, in a certain sense, don't exist at all. If we understand the proper nature of a matrix, then there are no zero eigenvalues, because a zero eigenvalue simply means that the matrix doesn't operate in a certain space or in a certain dimension of the space. So if we, from the very beginning, restrict the matrix to its own operational space, then the zero eigenvalues drop out completely, and then there is no such a thing as a singular matrix. So in my discovery, which came out in 1960 in the Mathematical Association Monthly, I have shown that an arbitrary n by m matrix, and I consider one of my interesting mathematical discoveries, can be resolved into three factors. The first factor is orthogonal. It is and there is, in addition to n and m, another number coming in r, which is the rank of the matrix. So we have, first of all, an n by r matrix, then an r by r matrix, which is diagonal, and which has only positive coefficients, only positive, no zero, only positive coefficients, and then again an r by m matrix, which is again orthogonal. So that you can resolve an arbitrary matrix, n by m, even if it has only one single element. Any matrix which is not the zero matrix can be written as an orthogonal matrix U times diagonal matrix lambda times the transposed of another orthogonal matrix V, U lambda V transposed. And that is an interesting decomposition theorem, which is of very general value. For example, one of the interesting consequences, which you show immediately from this decomposition, that if you take an arbitrary n by m matrix A, and if you take A times A transposed, which is a symmetric matrix, or A transposed A, that both of these symmetric matrices have the same non-zero eigenvalues, that they all agree. That's not easily shown generally, but with the help of a decomposition theorem, it falls out of the bag immediately.
These decomposition theorems are very elegant, aren't they? And
I think
feels
so.
that they are very fundamental.
I
must say,
so,
when
yes.
I listen to you talking about matrices, I see a definite light in your eye.
Well, that is true. That is true. I mean, I found that these things were really very elucidating.
Yes.
And you usually don't find these representations because people say, be afraid of singular matrix, you can't invert a matrix, and so on. But with a proper understanding, every matrix has an inverse.
Yes.
And
yes.
So that to any given matrix A, there is a unique matrix A to the minus 1. And the whole secret is you have to consider the matrix only in its own operational space and not outside.
Yes.
If you understand that, you understand a great deal.
Yes.
You,
Now,
had,
sorry.
you had already made contribution to matrix theories way back in 1950, of course.
Oh, I see. Yes. I mean, of course, this eigenvalue problem interested me a great deal because in Boeing one encountered this eigenvalue problem all the time. And the traditional methods, they give you, it was easy enough to get asymptotically the highest eigenvalue. But the question is, how could you get all the eigenvalues and eigenvectors of a matrix in such a way that you shouldn't lose accuracy as you go to the lower eigenvalues, because it's tremendously difficult to keep out the vitiating influence of the high eigenvalues on the very low eigenvalues. And then Professor Rosser, who was at that time in charge of this Institute of Numerical Analysis, where I went after Boeing. I mean, I worked a great deal in Boeing, but this discovery with the eigenvalues and eigenvectors of a matrix for a symmetric n by n matrix in only n steps, that's the minimum number of steps, which was the first method of this kind, I worked out at the National Bureau of Standards. And he gave us, to various people of the staff, a certain numerical matrix, and the question was to find the eigenvalues and the eigenvectors of that matrix. And I had a certain procedure, and I had a computer, a Negro girl who was absolutely marvelous in computing, tremendously intelligent. She never studied any mathematics, but you could count on her calculations to the last dot. And I will never forget when we had this, I think it was an 8 by 8 matrix, and to find out. And the eigenvalues varied in something like 10 to the 6, I mean the highest to the lowest. And I expected that the highest eigenvalues will come out to 10 decimal places, and then we gradually lose accuracy. But actually all the eigenvalues came out to 10 decimal places. I mean, this was a tremendous thrill to see that, that we didn't lose anything of course, it had to require the careful reorthogonalization process, which makes my method practically, let's say, of less value, or perhaps even of no value. But with this constant reorthogonalization process, you didn't lose anything in accuracy. And if you used a trial vector which didn't contain even any of these elements, because after all, a trial vector may be accidentally orthogonal to one of the eigenvectors, so then you would never show up. But the rounding errors always bring it in, so that somehow all the eigenvalues and all the eigenvectors came out up to the end with the same accuracy.
Actually, it's coming back into use again now, of course. There's been a paper this summer about bringing it back again, yes.
Well, I was very much thrilled by that. And I presented this talk on in a Boston, in a colloquium on numerical analysis in 1952, I think.
Was it the influence of the aircraft industry that caused you to be interested in curve
I think
smoothing?
so. I think so. I mean, the tremendous importance of the... I knew, of course, from theoretical physics that eigenvalues and eigenvectors, I mean, wave mechanics, everything is eigenvalues and eigenvectors. Only in this case, it was numerical. And in Boeing, when I was frequently asked to give lectures, one of the lecture topics was matrices and eigenvalues and linear systems, so that I was familiar in a theoretical way of the behavior of linear systems, particularly large linear systems.
And curve smoothing, did that come at Boeing as well?
The curve smoothing was, of course, very important, because curve fitting was one of the basic topics what engineers needed. And I think I made at least 80% of my salary on showing them how to do curve fitting with the help of Fourier series in a very efficient fashion.
Yes. Now, you mentioned the name of Fourier, Professor Lanczos, and I know that my colleague Morris is very keen to ask you about Fourier analysis. Morris.
Yes, thank you. Professor Hopkins said before that when you were talking about matrices, he noticed that your eyes lit up. I'm sure that you have an equal affection for Fourier series.
Yes, for Fourier series, yes.
This topic has always fascinated me in particular because it seems to pervade so many different areas of mathematics and physics.
Absolutely.
It has application in the statistical analysis of stochastic processes. It has applications in functional analysis and in electrical engineering, in communications engineering, and even in theoretical physics. I wonder if you would like to say what you feel to be the fundamental reasons why Fourier analysis, which after all really depends on the concept of frequency, why is this particular technique of such enormously wide application?
It is really almost like a miracle. You know, once Victor Hugo, the great romancier, lost a daughter who was of whom he was tremendously fond, and he was in a very desperate state of mind. And then he read the book of Job, and when they asked him, he said afterwards, if they would ask him, if he would ask me to destroy the entire literature and just keep one single book, I would keep the book of Job. So I would say, in analogous fashion, if all mathematical inventions would have been blotted out, keeping only one, I would say the Fourier series. Because the Fourier series, as I think the reason is that it is an orthogonal set of functions, which is of tremendous importance. But at the same time, the zeros are so wonderful that they are uniformly distributed. So I think if we wouldn't be so fond of equidistant observations, then the Fourier series would not have such a predominant role in applied mathematics. But in view of the fact that we very often make uniform, really that means equally distributed observations, whether we use a clock or any other instrument, but the most natural thing is to space our observations equidistantly. For equidistant curve fitting, there is nothing else that could compete with the Fourier series, because they are automatically orthogonal with respect to equidistant spacing, and none other functions can do that. I think I thought of these questions very often, but I thought to explain why the Fourier series, just the Fourier series, is so tremendously important from the standpoint of smoothing, curve fitting, and statistical operations. I think it is connected with the fact that the zeros, that means if the question is to distribute our observations in the most efficient fashion, then for any other function system you would have a highly sophisticated and highly pathological distribution of points. But for the Fourier series, the uniform distribution is the natural one.
Yes,
and I think I would explain it on that basis, that we are so fond of uniform observations, and that is the natural set of points in which we should observe if we use Fourier series.
But as you were saying before, there are other orthogonal families of functions.
There are other orthogonal functions, yes.
I was wondering more about the physical implications of using Fourier series to represent functions.
Yes.
It would seem that whenever one uses a Fourier series, you are really saying that somewhere in this problem, the concept of frequency is important. It has some meaningful physical interpretation.
Yes, that is true. Because it is such a simple thing in analyzing a function in terms of frequencies. Yes. And now the analytical functions have the property that their spectrum converges rapidly if we use the Fourier functions for the representation. If we use any other function for the function system, then their spectrum would decrease not so fast. It would decrease slower than if we use Fourier series in a certain finite interval, of course, in a certain given interval.
Yes.
And this maximum convergence of the Fourier series, of course, the drawback is that the functions are not periodic, and then what causes the non-convergence of the Fourier series is that the non-periodicity of the functions. But we can help that by making it periodic with an auxiliary set of functions, provided that we know the end values, and then only analyze the rest of it.
Yes.
So this way we can make the functions very amenable to the Fourier analysis. Mm-hmm. But there is perhaps a fundamental, a mystical kind of interrelation between Fourier series and the physical world, which makes it so tremendously amenable, which goes beyond our mathematical capacity. But the fact is that it's a series which is eminently practical, and at the same time has such tremendous mathematical and purely analytical properties that it is the best investigated series of all infinite series, the Fourier series.
I've heard it said that the notion of frequency is important physically because it's important mathematically and not the reverse. One would imagine that you could say it was important mathematically because it is important physically.
Yes.
But I've heard people argue in the reverse direction. Do you have any views about this?
Well, I really believe that the mathematical interest is wider than the physical interest. But if we look at all the functions and all the analytical functions which have been investigated, they were all functions which had some kind of application, like the Bessel functions, or any of these polynomials, the hypergeometric series. Well, basically, if you take Gauss's hypergeometric series, I think 60% of physics is already included in this hypergeometric series. Now, you might say, why? Isn't it a marvelous intuition of Gauss to introduce this f of x alpha beta gamma? Why just, I mean, he could have left out one of the parameters, or he could have put in more, but just this f of x and alpha beta gamma, all the three are necessary. If you have already this, it's already such a tremendous variety of functions that anything we need in mathematics, in physics, is somehow the hypergeometric series. Now you might say, why? Yeah, it just shows the intuition of a great genius, that he just finds not too much, not too little. He finds exactly the right mathematical determination which defines these functions and their properties. And lo and behold, you find in the physical universe that they are in some form realized somewhere. I mean, we find actually examples for the hypergeometric series somewhere in physics to any one of these functions. It's
Even
amazing.
Statistics.
It's amazing.
It is amazing. Yes.
Absolutely amazing. Why just this f of x alpha beta gamma?
I wonder now perhaps if I could turn to a somewhat different topic. I'm sure I can spare your blushes if I say that you're generally regarded as an outstandingly good lecturer and expositor of mathematics. Now, do you believe, as some people do, that outstandingly good mathematics lecturers are born rather than made?
I can only answer that the reason I became a good lecturer because I was a very bad lecturer. When I started my career in Germany, and I had a small group of graduate students, and I lectured on some very advanced topics of mathematics, completely wrongly, because I didn't put myself down to the proper level of the students. Then I watched their faces, and I noticed that they just don't grasp at all, and the whole thing was just tedious nonsense. But when I then came, I was only for a short time actually a lecturer in Germany. When I came to the States, I made it to a point because I realized that my whole career depends on good lecturing, that this is an absolute necessity. And I prepared my lectures very carefully. I still believe that the real secret of good lecturing is to prepare yourself, not in slogans, but to write out the whole thing. Up to now, I always write out. If I am invited to give a lecture, I talk freely, but I write out the whole thing in longhand. So then I have it at least. But this preparation, this longhand preparation, is, I think, a very important contribution to good lecturing. Then I learned, for example, in the States, that because in the States they are remarkably good orators. I don't know why, but it is a fact. They say you should start out by talking to the gallery, they say. In other words, you start out with a little anecdote, a little joke, you know, because the people get electrified and they get interested. Yeah. Otherwise, they might fall asleep. But if you catch them in the beginning with something interesting, you know, with a human touch story, then they will listen to you. And to this, of course, you have to put in the proper gestures, the proper acting and all that. But I learned that from a long experience as lecturer at various universities. So I automatically came into this habit of good lecturing, I think not out of a native ability, but by investigating what is good lecturing and doing and imitating that as well as I could.
Do you feel that any two mathematicians, if they wanted, could become equally good at lecturing? Or do you feel that some people
No, I don't believe that. You have to have a certain proper mixture of introvertness and extrovertness, I think. Even if you are an introvert, but you have to be able to imitate the behavior of an extrovert in order to be a good lecturer. I have seen, I mean, you take a man like Dirac, for example. He's a wonderful man, a great genius, you know. But he would never be a good lecturer, I think, because he's too much wrapped up with himself and cannot get out of himself. Now, I always considered it one of my strengths that I could project myself. Not only that lecturing, I project my voice, yeah, but I could project myself in putting myself into the position of another person and seeing it with his eyes and not my own eyes.
And seeing their difficulties.
Yes, and trying to understand the world with his eyes. Yes. And so that if I had to give a certain lecture, I always inquired now on what level. What is it, an undergraduate audience? Are they laymen? Are they townspeople? What? Because you can explain the same thing on various levels. You have to know, first of all, who is your audience. Because you cannot talk to to a faculty in the same way as you would talk to undergraduate students, and vice versa. Now, if you know who your audience is, if it's a mixed audience, you find a middle ground, or you find the lowest denominator, but anyway, you can make any subject, to my feeling, interesting without a technical language. I have used very often in my career as a lecturer or a professor in these various universities, if the student rattled down a formula, I say, tell me this formula in words. Don't use any blackboard. Don't use any symbols. Tell it me in words. Then he noticed he didn't understand it, but the whole thing is, if he would have understood it, he could have said it in words. And that is where you can get lost in formal details and where you become formalized, which I always tried to avoid.
Yeah. Do you adopt the same approach when you're writing textbooks?
And when I wrote books, I found that most of the books are written in an intolerable fashion. Most of the textbooks are terribly dull because the writer of the book automatically puts himself on a certain pedestal, that he's handing out wisdom. Now I say, why not talking to your audience as if you would be face to face to him? Why not in a natural way? And I think that goes back to the peculiar fact that I knew very little English when I came to the States. I had to learn, first of all, English. And then when I wrote down my lectures, and I had a friend of mine who was always going through and said, what did you want to say here? I say, I wanted to say this and this. Why don't you say it that way? Then I noticed that instead of using a rather cramped official formulation, you could just as well use it, you should just as well use a more chatty approach without being too verbose, but express it in a way as you would talk to a friend. And by that, using this more informal, this more conversational kind of style, I found why not take that over into writing books? Why not talk in a conversational way? And why is it not allowed to put in a certain emotional emphasis? If you are enthused about something, why don't you say so?
Yes, it seems to me, Cornelius, that you've rediscovered something. If you look at the collected works of people like Rayleigh and Stokes, these very famous mathematical physicists of the Victorian age,
yes.
19th century, you'll find that they wrote in a much more leisurely kind of fashion. I'm paraphrasing, but I can quite imagine that Rayleigh would, or perhaps Osborne Reynolds even better, would open a paper by saying, last Sunday it was a very fine morning, and so I decided to do an experiment that I've been wanting to do for a long time in my laboratory, and so he would continue in this kind of fashion.
Yes.
Now, yes. I can certainly see that if one is writing a textbook for students, or an advanced textbook, say, for postgraduate students, there's a lot to be said for taking the sort of viewpoint that you've been expounding. But I think there are difficulties when one gets on to what you might call the research monograph. This often tends to be written in a very stilted kind of fashion,
yes.
Usually with great economy of words and space and all the rest of it. And it's difficult to get the same kind of informality. I don't know if this is unavoidable or not.
It is absolutely true. I never wrote those kind of monographs, which have to be complete, which have to contain the entire bibliography yes. of the subject.
Yes.
I didn't care for completeness because I always wrote on topics with which I was familiar.
Yes.
I always thought that if somebody who writes a book writes on something in which he's not completely at home and in which he did not do work himself, then he will not succeed in everything. Therefore, this question of completeness was out. I mean, for example, if I take this Space Through the Ages, which is the last book I have written
yes.
by the academic press, which was actually a great success on the market.
Splendid.
This is not complete. I mean, who could write a complete history of geometry? It's completely out of question. But it is complete in a sense because if we restrict ourselves to metrical geometry, as far as metrical geometry goes, all the important chapters of metrical geometry are included in the book. Yes. And it's not a question, I didn't want to write history of geometry, but the evolution of geometrical ideas. And then it's not important to what extent it is complete, not even important to what extent it is scholarly. The question is, are you able to convey this enthusiasm which the people felt who developed these geometrical ideas, like Euclid, or Pythagoras, Euclid, or Bolyai, or Riemann? I mean, if you are able to convey that enthusiasm and to show what I like to call the inner must, that means the inner necessity of a certain idea, then you have written a good book.
Yes. Now, you've just been mentioning some very outstanding names in mathematics, and one might also mention the names of Archimedes, Euler,
Yes.
Bernard Riemann, Galois, and so on.
Yes.
We, in mathematics, we're very lucky, I think, in having had a whole galaxy of talent, really outstanding and brilliant people. Now, if you were asked to pick out usual sort of question that one might put to a person in a discussion of this kind, if you were asked to pick out 2 or 3 of the greatest names, what names
Of the
would
greatest
you,
names.
what would you choose?
Yes, I would.
This
I
must
would
be
certainly.
personal, of
I would
course.
include Archimedes.
Yes, number 1.
I would include under all circumstances Archimedes.
Yes.
And then I think one couldn't leave out Euler, who was a tremendous figure in as much as he knew so much. I mean, he's
Yes.
a tremendous
Yes.
algorist and a man of tremendous capacity. So Euler should also be included. Then I think Gauss cannot be left out, because what Gauss has done, that is absolutely unbelievable. Now, you might say, well, but suppose we would have the perspective of hundreds of years, maybe we would choose somebody of our, maybe Johnny von Neumann or somebody. But I'm not sufficiently familiar with their work, and I do believe that to create, for example, such an edifice of thought that Gauss has created,
Yes.
that is something unbelievable. But on the other hand, for example, from the standpoint of pure ingenuity, maybe Riemann was even greater than Gauss. But he didn't have this tremendously wide field of interest.
Riemann was extraordinary. His collected works
It's only
fill a
about,
volume of about
yes,
this size.
about 250 pages.
But every paper was important.
Every paper was important, yes. And that was not known in a short time.
No, this is unusual,
It's
very,
very
exceptional.
unusual, yes. He was
Riemann died relatively young.
very young, in lung
Very young.
disease. And in addition to that, he was always in the shadow of Gauss. That's why we must not forget that.
Yes.
He was also in Göttingen. And Gauss was very good to him, by the way, but he was always somehow in the shadow of a great man.
Yes.
And so he was not recognized to this tremendous genius that he actually was. For example, the prime number theorem, zeta function, and the functions of a complex variable. I mean, it's fantastic what he has done. And then the Riemannian geometry, the idea of the Riemann surface. I mean, these are tremendously ingenious ideas. Everything that he picked, there was a genius touch, an ingenious touch in it.
Yes.
So I have a tremendous admiration for Riemann.
Yes. It very often seemed to me that if you take these people and some of the things that they did, in a sense they were successful because they hit either immediately or perhaps ultimately on the right kind of notation.
Yes, yes, the
I think as
notation.
a schoolboy, first coming across the Jacobian notation, being at once struck with the sheer brilliance of this notation,
Yes.
because it suggests automatically,
operation-
of course,
it's operational.
what is how 2 Jacobians will multiply themselves together.
Yes.
And there are other examples of this kind. In more recent years, of course, we have matrix notation being very extensively developed, the tensor notation with all these superscripts and
yes,
subscripts,
yes.
which is tremendously
Tremendously
economical,
important.
and it packs a lot of information into a small amount of space.
Yes. The matter of notation is absolutely, I mean, Leibniz was aware of that. Leibniz was the great...
Whereas Newton was not.
No, Newton was not
No.
aware of it. But Leibniz, and the notations of Leibniz are used up to our days, because they're functional. They're tremendously functional. And Leibniz
Yes.
was aware of the importance of a notation,
Yes.
whereas Newton didn't pay much attention to it. And this functional notation was of tremendous importance, for example, in tensors. I mean, if we wouldn't have the subscript notation, we would be lost. And yet people
Yes.
thought, why should we have subscripts? Couldn't we use the tensor as just capital T as an operator, which
Yes.
looks good enough, but if it comes to working out problems, you are lost.
Yes.
And so it is by no means self-evident that you use the subscript notation. And it is, if you read Lagrange, even analytical mechanics, and you go back to these original publications of the Poisson bracket, I had to do that recently.
Oh, yes.
The Poisson bracket, I mean, it is dreadful even to read the paper, because instead of using I and K or so, they write out A, B, C, D, dot, dot, dot.
Yes.
And then alpha, beta, gamma, delta, dot, 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 and I mean, it's hopeless.
The Christoffel symbol, incidentally, seems to me, in retrospect, not quite right. Would you agree?
Well, that is accidental, that it doesn't fit the position of this. But I mean,
It's
it
a
was
little
an
awkward.
excellent idea
Yes.
to call it that way, this
Yes.
IJK notation. It was
Yes.
a nice, very nice notation, actually.
It's on 2 lines. I suppose that's why I don't
It's in
like
2 lines is important. Of course, nowadays you write a bracket IJ, comma, K.
Yes,
But the fact that you
yes.
put it in a separate line shows that it has a different function from the
Yes.
other 2 indices.
Yes.
So to put these 2, because it's symmetric in I and K, to put them in one line is very clever. And then below that, it was a good notation.
Yes.
I think your interest in notation comes out at the beginning of Numbers Without End, where you go to so much trouble to point out the different schemes for multiplication, division. In
Yes,
all
I
the
had to do that
countries of
because
the
every
world.
country has
That's
its own. And for example,
Yes.
the American habit and the English habits are just opposite as far as decimal point and multiplication goes.
I think that's probably the first time any of us have seen it written down.
I see.
so many
Because you take
notations.
it for granted.
Yes.
Yes. And also what they call the comma. In Germany, they call it not the decimal point, but the comma. And they denote it by a comma, which is a good idea because actually the comma is not used for something else. The dot is used for decimal point, also for multiplication. So the comma notation would not be bad.
And talking about notation, you were discussing before there's a modern approach in mathematics of being extremely abstract and formal. Now, this
Yes.
particular approach itself has engendered a certain type of notation. The notation which pure mathematicians use in many fields tends to emphasize the abstract way of thinking.
The abstract way of thinking, yes.
Do you feel that
Yes.
they have made a mistake, in fact, in emphasizing their abstractness by entrenching it in the form of notation?
Well, I feel that an abstract notation can do a lot in simplifying a proof or to bring out the essence of a proof in the simplest possible way. But the danger is that it can hide the difficulties. If you would actually apply this abstract notation to an actual problem, then you see that you have to do much more than what is indicated in the notation. If possible, to my feeling, an ideal notation should indicate all the actual operation you have to do. That's so beautiful in the tensor notation, where now, of course, you had the trouble that you had to put those sigmas in front when you had to sum. And people never cared for studying tensors essentially because these many sigma signs made them crazy. And then Einstein came in with this very beautiful sum convention, which is nowadays used, so that a tremendously complicated sum looks like very simple because you leave out the sigma signs. But that was a notation of tremendous elegance, because the fact that you sum from 1 to n is automatic, so you didn't have to put that out. And the fact that you sum is indicated because you have 2 indices. So this Einstein sum convention is one of those landmarks in the history of mathematics where a very simple trick had enormous consequences, because I think people would have never studied absolute calculus and tensors and Riemannian geometry if you would have to put out all these tremendous number of sigmas in front of the formulas.
Yes,
but
this is
leaving
very
them
true.
out, it becomes and yet you know what you are doing. So it is not overly abstract. Because if you look at it, you still know that you have to sum. If it comes to an actual
Yes.
calculation, you have to do all these sums.
It's a shorthand which
It's a
you can
shorthand,
unpack if needs
Unpack.
be, but
But
normally you
everything
don't.
is indicated, because
Yes.
the fact that you have 2 equal indices, that indicates already that you have to sum. And the fact that the sum goes from 1 to n is axiomatic, of course. So that is a very beautiful example of an ingenious notation which starts out a new era in the history of mathematics.
Yes.
I don't know similar examples in modern mathematics because I'm not sufficiently familiar with modern mathematics.
You've had a great interest in history of mathematics, haven't you?
Yes, the history of mathematics always interested me because in presenting a subject, I could never see how you can present a subject without giving at least a background, without a historical background. I always did that because you can't use this method of Pallas Athene jumping out of the head of Zeus, in full armor. I mean, that is something that the student doesn't take in. But if you go through, in a telescoped way, if you go through the individual mind, you repeat what the race has done through hundreds of years, then it becomes deeper. I'm always afraid in our present educational system that we teach too many words instead of concepts. A student doesn't learn ideas and concepts, but essentially words, and tries to remember formulas. but he doesn't connect the formulas with their inner meaning. I always think that if you say, do you understand? He says, yes, I understand. What does it mean, I understand? You can understand something from the outside, and you can understand it from the inside. And that makes a terrific difference. Most people, if they say, yes, I understand, they understand a certain problem or a certain situation from the outside. But they're unable to see it from the inside. And it cannot be done at once. I mean, it takes some time to sink in. And nowadays, the student doesn't have the time. In my time, I could take plenty of time because the syllabuses were so much shorter. But today, when so much is expected, that the student runs from one subject to the other, and he's responsible for so much material, the human mind, the capacity of the human mind biologically doesn't improve. So what do? Understanding changes from an inside job to an outside job. That would be my criticism against the present educational scheme.
Would you not feel that this is useful, even if students have only a superficial understanding of a certain area of mathematics? Do you not feel it's possible that the more they live with the ideas and the more they work with them, their understanding?
That is certainly true. It's certainly a gradual process. There's no question. A student who first learns calculus would not have the same understanding as if the same thing comes in his graduate years. But I would still say that at least he should have, if you ask him, for example, in a limit, could you describe what is a limit? Then he should not just repeat a formula with epsilon and n, which he doesn't understand, but maybe give an illustration of a limit process. And I say, fine. You see, you really understood. You don't have to know all these exact definitions, but an idea how we approach something more and more with an arbitrary accuracy. I mean, then I see, aha, yes, he understood what he's doing.
What do you think we should try and do in training students? Should we try and give them a deep knowledge of a small area of mathematics?
I would prefer that. I mean, I should say I would cut down on the syllabus a great deal. Because after all, who decides this is important, this is not important? For example, cutting out geometry, because it's not important. Why? I mean, I think geometry is a tremendously enthusiastic subject. And I always enjoyed geometry, even as a high school boy, much more than just algebra and formalism. Why cut it out? I think it's a great pity. So the syllabus is today too difficult. It tries to do too much. It's my opinion. I may be wrong. And certainly I would cut down. But instead of that, I would insist that the student, what he does, he should really understand. Even if he cannot do the problem. But he should understand what is the problem.
Well, Cornelius, we've covered this afternoon a whole range of topics.
Yes.
Particularly bearing, of course, on the things that you've been interested in. And I should like to thank you very much, Morris, Ronald, and myself, for being with us today in Manchester and for us to have had the opportunity of talking to you about mathematics. It's always seemed to me, and increasingly since I returned to university from government service elsewhere, that it's very important to talk about mathematics.
Yes.
People, often one's closest colleagues, I think, are often not all that keen really to talk to one about mathematics. And this, I think, also applies to students. It's very difficult to get many students to come and talk to one about mathematics in a very informal kind of fashion. And I'm sure they find it equally difficult to talk to one another in an informal fashion. And I think this is important. I mean, to, if you like, take the subject down for a time, a peg or two, and talk about it in a very informal fashion. I think often this is the way in which new viewpoints, new ideas get born, and you can give a new twist to things, and you go back refreshed, and so on and so forth.
Yes.
Now, I think probably you yourself have never had a great deal of difficulty in talking about mathematics, but if we can go right back to your undergraduate days in Hungary at the University of Szeged, if I'm pronouncing it correctly, which I'm probably not.
Szeged, yes, that's right.
Were you able, I suppose you were a lad of 18, 19, something of that kind. In those years, were you able to talk in an informal fashion about mathematics?
Well, we had these so-called seminars in addition to the formal lectures.
Yes.
We had lab exercises, for example, in calculus, where certain problems were given and we came together and there was the instructor and he asked various questions, or he called out somebody to the blackboard and I was often called out. I had a chance to explain to certain things in mathematics, and I was very, very lucky in that. Already in secondary school, I had a it was a Catholic gymnasium, and that was a teacher who was a very excellent man, but he fell in love with a woman, and he was always terribly sleepy in the morning because they drank too much. And then he called me out and said, now you take over and you explain to the people what the number I is and such things. Well, I enjoyed that tremendously.
That's a very amusing anecdote.
And so it was a good introduction for me. I mean, I liked this professor very much, but it was just his weakness. He couldn't help it. And so it was a great opportunity to learn. If I knew, I'm going to present it to the class. And we also had discussions with each other, certainly. That is, to my feeling, discussions are of tremendous importance. But if I may point out that we had here a question-answer period which worked out very harmoniously.
Yes.
But the fact is, it was a picked group, isn't it? I could very well imagine that there would be 4 people.